All right, so good morning, good afternoon, everybody, and welcome in from around the world as we enter into another exciting Exploring by the Seat of Your Pants broadcast. My name is Jesse, and I'm your virtual adventure guide here today. It has been so thrilling over the last few months bringing over 70 programs featuring scientists and explorers to kids like you around the world, so thank you all so much for joining us as we continue to showcase and celebrate such amazing people and places around the globe. Now, every one of these talks is on our YouTube channel if you want to check that out. We've got over 2,500 past broadcasts there as well. Now, even with our standards of sort of bringing in some of the coolest people on this planet, astronauts, cave divers, zoologists, and more, we've had a very special series going on over the last month, and today it continues. Now, this is our McMurdo Lidar series in conjunction with the amazing team at CIRES. So if you've had the chance to check out Ian or Jackson's presentations in our last few weeks, they are really, really special. I can't encourage you to check them out enough. And we've got one more to wrap up our series on November 15th, a very bittersweet day for us all here at Exploring by the Seat of Your Pants. Now, I'm going to turn it over to Daniela Pennycook to explain a little bit about what CIRES is before she leads us into our speaker, Yingfei, joining us live at McMurdo Station. So, without further ado, Daniela, thank you so much for joining us today, and tell us what this whole collaboration is all about.
Awesome. Hi, Jesse. Thanks for having me today. It's so nice to be here with all of you joining us. My name is Daniela Pennycook. I work for CIRES Education and Outreach. And CIRES is the Cooperative Institute of Research in Environmental Sciences. We do research all over the world. There are 850 scientists studying the environment and studying climate. Yingfei Chen, who's going to be speaking to you today, is one of those scientists. He's a grad student here at CU Boulder. And CIRES, the cooperative part, is our relationship with NOAA, the National Oceanic Atmospheric Administration. So we work really closely with them to provide high quality climate research and environmental science to all of you. Today, we're joining you from CU Boulder, and we're excited to connect with you all. So I'm going to turn it over to Yingfei Chen.
Fantastic. Thanks, Daniela. And Yingfei, welcome to the broadcast, man.
Yeah, this is Yingfei.
So I know we talked before we went underway live, but we have 93 groups joining us from, I think, 15 states, provinces all over Canada, Germany, Egypt, India. It's a really exciting audience. And I know you've got a lot to share with us today about the upper atmosphere. And so if you want to dive in with your presentation, you can take us away. And then we're excited for questions at the end.
Sure.
Awesome, man.
So you guys can see my screen, right?
Yeah, you're perfect. You're good to go. If you want to drag the little banner on the bottom that says StreamYard sharing your screen, yeah, you can get rid of that. Perfect. You're good to go.
Yeah, so thanks for Jesse and Daniela for introducing me. So I'm going to give the talk today about the introduction to upper atmosphere. So let's get started. I'm going to introduce 4 different sections today. So the first is about introduction part, which is about me and our group. The second part is about the upper atmosphere part, and I'm going to introduce where it is and what happens there and why do we need to study it. The third part is about the LiDAR equipment, which is how can we study the upper atmosphere. And the last part is about questions. So first, introduction part. About me, I'm a second-year PhD student in aerospace engineering science at University of Colorado Boulder. And I'm working with Dr. Xingzhao Chu. She's pretty great, and she's an expert in the LiDAR science, I would say. And the reason why I joined this group, because University of Colorado Boulder, they can combine the aerospace engineering part and the science part pretty well. And Dr. Xingzhao Chu, she's pretty good at introducing all the science with those atmosphere engineering part, and we can run the LiDAR in McMurdo in Antarctica. That's why I became one of the team member of her group, and I'm going to become the McMurdo Winter Over Scientist for the year 2025. Here are just my personal pictures, and you can see all the cool mountains at the background, and you can also see the McMurdo Station, Antarctica here. Yeah. Then I'm going to introduce the upper atmosphere part. So let me introduce the layers of the atmosphere first, because we got 4 most important parts of the atmosphere, starting from the troposphere, and then is the stratosphere, and we got the mesosphere and the thermosphere. Then all the way up, we got all the exosphere there. So usually we decide those different layers based on their altitudes. And you can see from the ground to about 20 kilometers, we call it troposphere. Usually all the passengers plane stays there. And then from the top of troposphere, we got all the way up to about 50 kilometers. That's all the stratosphere. And then above the stratosphere, we got all the mesosphere. Then it's the thermosphere. So another thing we need to check is here. I got this like more science figure here, because we can see this black curve, which is the temperature of the atmosphere. Like say in troposphere, we got those temperature. When we get higher, those temperature just get colder. While in the stratosphere, it's opposite. When we get higher, those temperature can increase. Similar thing happened in those mesosphere. When we get higher, those temperature just decrease to the minimum here. And then in those thermosphere, the temperature just increase rapidly, and a lot of things is going on there. And that's why I have to introduce this part, which is the complicated ionosphere. Usually we got all those electron density there, and we just decide those layers based on different parts. We call it one is E layer, and the second part is the F layer. Then I need to introduce you guys, why do we need to study those important ionosphere? So you can see in this figure, the red box just say it's where the ionosphere is in the upper atmosphere, and usually it's from the middle of the mesosphere up to the magnetosphere, and they got daytime and nighttime variations. During daytime, those layers just circle due to the solar radiation, and during nighttime, mostly those ionosphere just collapse due to the lack of interaction between the sun radiation and the atoms in the thermosphere. Usually, those ionosphere got a lot of relationship with those communication part, because we can use those ionosphere to refract all the shortwave radio waves, enabling long distance communications. And at the same time, the solar flares and the storms can cause changes in the ionosphere, and that can cause errors in the GPS signals. And usually they can just shut down the communication between all the stations and the satellites. That's why we have to study those upper atmosphere, and including this ionosphere here. Next part is I'm going to introduce the motivation to study the upper atmosphere in much more detail. Like studying those atmosphere, we can understand the climate change and the trends there, and we can improve our communication from ground to, say, like station and satellites. And then we can also plan our satellite mission much better and manage all the space debris. Also, we can assess the risk of disruptive space weather. For example, we got all the magnetic storm. Sometimes they can just cause many challenges in those communication between ground and all the space station. So the relationship between the upper atmosphere and the climate change is complex, and usually the lower atmosphere is warming up while the upper atmosphere actually is cooling down. So it's very complicated. That's why we have to do more science there. So how to study those upper atmosphere? Actually, from because we are the Lidar team, we just use the Lidar equipment to do the ground-based observation of those upper atmosphere. But through what kind of tracer we use those metal species in the upper atmosphere? You may wonder why those metals can just stay there, like say form a permanent layer there, because the principal source of all the metals in the upper atmosphere is the ablation of the meteoroids. All the meteoroids, they just become cosmic dust particles when they enter in the atmosphere, and they can stay, say, like between 80 kilometers to 105 kilometers, and they can form a permanent layer there all the time. That's why we can use those metal species as tracers through the LiDAR equipment to do some research. So next part, I'm going to introduce the LiDAR part. And you can see the picture on the left is pretty cool. We got the laser beam shooting directly to the sky, and we got auroras at the background. So the LiDAR equipment, actually, it's the light detection and ranging. So LIDAR, we call it LiDAR. The basic principle is kind of simple. We just send a light to the atmosphere or other medium, and then we record the light scattered by those medium and the atmosphere as a function of time, and we just get those return signals. And then we use the some equipment to convert all the time of flight to distance, just following this simple equation. We just can calculate the altitude or the range based on the time of flight. So the objectives for those LiDAR light detection and ranging is we need to quantitatively detect all the metal species, and we need to calculate the temperature and wind profiles based on that, and solve some fundamental science questions. Like this GIF here, you can see, we just shoot a beam out, and it got returned to our telescope. Then we can check all the signals. So for the equipment part, usually all the LiDAR system, they got three important parts, which is transmitter and receiver, and the DAQ part, which is the data analysis and the control part. The transmitter part, we just say, like, we got a laser transmitter. We can just shoot out all the pulsed laser to send out all the photons. And then they just hit this metal layers permanent in the upper atmosphere, and they can give us those signal back. We got all the receivers, which is the telescope, to collect all the photons. And then we got this PMT, which is the photo multiplier tube to transfer all the photons into electrical signals. And then using this DAQ part, which is data analysis and control part, we can just check on our computer to save all the data. And in the world, definitely there are different equipments which can study the upper atmosphere, but they all got pros and cons. For example, they got rockets, and they can just do very high altitude measurements, but usually it's too high, and those are very expensive. And then some people, they can, like NASA, they use the balloon campaign. They can just send the balloon in the air, and they can collect all the air sampling, those stuff, to do the research. And of course, we got all the satellites orbiting around the Earth, and they can do all the measurements. But LiDAR, actually, we can close one data gap between all the, like, say, balloon measurements and the satellite measurements. So we can cover the data gap between those guys, and we can give them the neutral information. Usually they can only provide those ion measurement and the electron measurement, but we can provide them with the neutral stuff. So I can show you more pictures about the LiDAR system. So this is me operating the LiDAR system. You can see all the LiDAR transmitter here with the cute yellow light, and we just do very like accurate alignment, and we can control the wavelengths pretty good, and we shoot the beam out. Definitely that's Dr. Chu's work, and she is very good at operating all the LiDAR system and making all the LiDAR system at their, say, like peak level, so we can get the most sensitive LiDAR system in the world. And then the middle picture, just like we can see all the auroras at the background, and we can also see this yellow beam, which is our LiDAR beam. We just say, like, the wavelength is 589 nanometers. And then this one is just our lab in McMurdo, and which is at Aurora Heights, actually, Antarctica. We can see our lab with the background of all the green auroras. Next, I think if you just shoot a photo directly to the sky, you can see the similar thing as I did. You can see the yellow beam with all the very amazing auroras, and you can see all the stars pretty clearly, and sometimes even the meteor trails, there. And then those are just the more pictures I took during this season, and those are the moving auroras with the yellow LiDAR beam. And that's pretty cool. And you can also see those meteor trails pretty clearly with different resolution, I think. Yeah. So next part is all the question part. Yeah, I need to thanks for Jesse and Daniela for helping me a lot for this slides, and also definitely Dr. Chu helped me a lot for operating all the LiDAR system, and she teach me a lot about those basic principles of all the lasers. And I also have to thanks Jack, who is sitting next to me with all the setup today, because I have to get a special laptop for doing this presentation. Yeah.
Well, Yingfei, thank you so much. And Dr. Chu is going to certainly be very thrilled with this presentation. I've never had someone praise their supervisor quite so much as you have. So that's wonderful and delightful today. I'm going to lead in with a few questions, and then our live classes, if you guys have questions, YouTube groups, if you want to identify yourselves and let us know where you're joining from. If you have questions, by all means, we'll do this for another 20 minutes or so. But my first question is, why have the LiDAR station in Antarctica? Is there a purpose for it to be there? Why not have it in a more accessible location where more people might be able to utilize it?
So in my opinion, why do we need to operate all the LiDARs in McMurdo in Antarctica? The most important reason is that in Antarctica, you got the long nights. Usually our LiDAR system got the best signal back when the solar background is minimum, which means we definitely prefer to operate during the nights. I mean the totally dark nights. That gives us the minimum background, and we can get the best signals in the world. And another reason I can think of is the McMurdo Station in Antarctica. Usually it's at the edge of the aurora zone, which is very active with all the solar Earth interactions. So we can see a lot of interesting stuff, those scientific stuff in this area. That's why we need to put our LiDAR station in this or by the edge of those aurora zone. And the third reason I can think of is the air usually here is pretty clear. You can see all the stars by your eyes pretty clearly. That means you don't have many smoke or clouds in the air, and we can just shoot the beam directly to the sky and to that metal layers to give us better signals. Yeah, I think that's the reason I can think of right now. Yeah.
Excellent. And I'm really curious about the edge of the aurora zone. So, I mean, a lot of our students today are joining from, we've got classes live in Florida, we've got classes in California. So they're unlikely to ever see an aurora. I'm quite a bit further north, and I'm at the lowest possible point that aurora seem to come down to. Is there a point that they stop, and why is that? Like, do we know why aurora are in one special band? Could you explain a little bit more about that?
In my opinion, it's complicated because you got a magnetic field around the Earth, and usually the field got some gap. So those actually auroras, they are just energetic particles. They can enter in the Earth's atmosphere through those gaps. Actually, makes those particles entering the Earth's atmosphere much more easily. That means you can always form a zone there, and they can enter the Earth's atmosphere much more easily. That's why you can always see aurora around this aurora zone, I think.
I really encourage our classes to look up the two bands in the Earth in the north and southern hemisphere, where you get the aurora borealis up here in the north, aurora australis down in Antarctica where Yingfei is. It's really special to see how basically when particles come from the sun, they hit the Earth and channel to these various regions, and you end up with these sort of rings of aurora belts. There's very certain places on this planet that are sort of the peak places. If you want to go check them out, you don't have to quite wing it so much. Great answer, Yingfei. Now I'm curious, you talked about overwintering there. So how many scientists are at the station when they overwinter? Or is this your first time doing this, or how do you feel about it all?
Yeah, for me, I'm going to be the winter over scientist in 2025. So not this season. This season, Jackson and Jack, they are going to stay here for the winter. And usually, I think during winter, around 300 people can stay on the station, and some of them are definitely scientists. They are going to do the more science stuff in the station, and most of them just the science sport people. They can sport all the science here in McMurdo. And I bet after this season, Jack and Jackson, they can give you more information about the winter over life here in McMurdo.
Well, hey, they can give you more information, especially because you're going to be the one that's actually down there living it. So you're going to get all the tips and tricks from them. But how exciting to end up in this position. And I'm so curious, as someone with your background and sort of the academic work that you've done, why choose Antarctica? Was it because it's the best place to study it? Or had you always wanted to go visit Antarctica or be a part and do science there? Like, how did you end up here where you get to be at this really special place?
That is a very good question because, you know, for me, I'm a Chinese, and usually it's very difficult for Chinese people to really make the McMurdo Station because it's a U.S. station, of course, and the most, like say, outstanding or advanced science happen here in McMurdo Station. That's why I have to be here to do some really real science with Dr. Chu, and of course, she can teach me a lot with all the lasers, all the science part. That's why I want to be here in Antarctica and to study the most advanced science. You can say all the instrument part, especially as a Chinese. Yeah,
Yeah, fantastic, man.
The most.
Oh, there we go. I'm going to head to our first class, Mr. Dupuis' class. If you guys have a question for us, you're up at the camera. Come on in. Hey, guys.
Hi. When you first started your job, was it hard to like understand some of the stuff? Because it looks confusing.
Yeah, I would say definitely, yeah, because all the topics we are studying right now is kind of complicated because it includes a lot of different interactions, all the chemistry, all the dynamics, especially in the upper atmosphere. It's very complicated, too much information involved. So for me, I think yeah, at the very first beginning, I was confused a little bit for all those kind of research, but gradually, after you read more papers and trying to do some research by yourself, like select your own topics and trying to form some science points, you may gradually understand everything.
I'm glad we got that question because the work that you do is very complicated. It's stuff that people, again, at the graduate level beyond end up doing on a regular basis. And so for students, if you're interested in this stuff, it always starts small. It starts with general science classes. It starts diving in with physics. It starts with reading popular journals, books. There's a ton of accessible books in this field, by the way, too, if you're keen on something like that. And then ultimately reading a lot of very scientific papers like Yingfei would be doing. Miss Evans' class wanted to know what metals are being detected. So you're shooting the laser up. Is there anything specific that you're looking for, or is it metals generally?
Actually, that's a pretty good question. That's the science part. So in Antarctica, we got two different Lidar systems. One is detecting all the sodium species. Another one is detecting all the iron species. But usually in the world, you can also do like, say, potassium. You can also like operate those Lidar systems with the specific wavelengths. We can detect all the potassium species, and we can also do that calcium, so which is Ca, and usually you can also do the Ca plus, which is the calcium ions. So we got a lot of metal species to study, but here for our LiDAR group, we operate the sodium LiDAR and the iron LiDAR at the same time. We can do the simultaneous metal species study. Yeah.
So, Yingfei, this is a very ignorant question, but this is half the fun of these programs. Why are there metals up there at all? Like, what puts them up there in the atmosphere? How can we find them up there in the first place?
Oh, that is a very good question.
Oh, I'm glad.
I don't really know how to answer that, but I think.
Go ahead. Yeah.
Yeah, they used to have all the rocket measurements, so they can detect that some metals just at those altitude range, and people gradually realized, oh, we got all the metal species at that altitude range, like say from 80 kilometers to 100 kilometers.
Yeah.
Then people try to use those metals as the tracer to study the upper atmosphere, because otherwise you got no like say tracers to get those information from the upper atmosphere. Yeah, I think gradually like people can form those
Discovered it.
LiDAR topic and doing all the research there. That's to my understanding. Yeah, I don't really know how to answer that.
Excellent. I always like when we can stump the scientist a little bit, because it's really, this is quite amazing that people even figured out that this is something that you could do, and then, you know, went to Antarctica, designed a giant research base and shot lasers at the sky, and it works out, and we can understand more about the world and universe because of that.
Yeah.
That is, I mean, science never ceases to amaze me, but that is particularly special. Miss Henderson's class, I'm going to come to you guys first, and then Miss Delgado, let me know in the chat if you're good to go, and I'll come to you right after. Miss Henderson.
Hi, my name's Maxwell. I have a question.
Yeah.
How does all like the LiDAR beams and laser beams work, and how do you keep yourself hot and like in the lab without the ice melting?
So how are we powering all this, Yingfei, and how are we keeping it warm? You're in this really, really cold part of the world. How do you even get this working at all?
Oh, like say, how can we maintain all the laser temperature? That's the question. Yeah, because first of all, the lasers right now we are operating is very powerful. We got like say a 1 watts, even 2 watts out of some of the laser transmitter, and the high power can make those lasers stay in a stable temperature area. And at the same time, we also tried our best to maintain all the temperature in our lab. We try to not to adjust any, like say AC or the air handler, those stuff, to just not to interrupt all the lasers themselves. But we tried our best to maintain all the temperature in the lab, because all the lasers, they are temperature sensitive. If you cannot control your temperature right, the wavelengths just can be shifted, and anything could go wrong in that case. So we just tried our best to maintain the temperature in the lab. At the same time, you know, those lasers are powerful, super powerful. Yeah.
So I have two follow-up questions on this, or one comment for our classes. One of the things that we've done in the Antarctic programs before is highlight that the main sort of profession down there is engineer. There's a lot of people that go to Antarctica to make sure that nothing breaks down, because there's a lot of people that live in Antarctica now. Over 1,000 people live there year-round. I think it gets to be 4,000 in the summer among all the Antarctic bases. And so a lot of people are there to make sure all the systems that keep those people alive, allow science like this to happen, are down there to do that. So if you're inclined to be an engineer in your life, you can do that in one of the most special places of the world, in Antarctica. And so Yingfei, you've been talking about how powerful this laser is, and Ms. Henderson's class wanted to follow up with this. So if we took this laser, instead of pointing it up, we pointed it at the ice, how do they not melt the ice? Like, would this melt the ice? What could we do with this laser if we wanted to? Or is it powerful? Is it not that kind of power?
I don't think you can just point our laser directly to the ice. I don't think that's allowed. Yeah, we got very specific policy to deal with. We have to make sure our laser only shoot directly up to the sky, because that makes everything not dangerous. We have to keep everything safe here, and we only want to do the science research here, all the ground-based observations part. Yeah, we don't want to hurt anybody, so we can try our best to keep our laser safe and try to give us the best science results. Yeah.
Of course, right? We don't want to be James Bond villains. We don't want to be shooting the laser at anyone in Argentina or elsewhere in Antarctica. That is not allowed. Okay, so there's your answer, Miss Henderson's class. So I'm curious, we got a question from Miss Delgado's class. I'm sorry you guys are having some tech difficulties, but they shared in the chat, Yingfei. We're learning about solar flares. We're learning about how the sun's atmosphere and the sun's sort of weather comes and impacts the Earth. Can solar flares destroy infrastructure around the world? This might not be your main area of expertise, but when we're studying the upper atmosphere, are we trying to understand and maybe prevent things like a solar flare from impacting the Earth, or how would that work? If you can answer that.
I will try my best. So, in my opinion, all the solar flares, they are not that strong though, but they sometimes can be pretty strong, and they can interfere all the, say, electrical signals we are observing. And in some extreme case, I think those solar flares can become disasters, but I don't think it's right now, because our Earth is orbiting in the regular circuit, and the sun is operating pretty normally, so nothing really dangerous could happen in the following few years at least. But who knows in the future what will happen? We'll see.
I encourage our classes that are interested in this to look up something called the 1859 Carrington event. So this is the ultimate sort of example of when a really major solar storm impacted the Earth in a negative way. And it was back in the era when people were in horses and buggies and there was very few electronics in the world. And it was quite impactful. So we are trying to study the sun and our atmosphere to understand how and when these events could happen, how we could possibly mitigate them here on Earth. But it's a very challenging sort of threat from space. Now, this question leads me to one, you talked about some of the reasons that we're doing this research. Are there concrete, tangible things that Earth benefits from to know what you're learning with this LIDAR system? Or is it knowledge for its own sake, just to understand more about our atmosphere? So basically, the research that you do, is there concrete things that, okay, now we know that, now it's easier to fly rockets to space, or now it's easier to understand solar flares? Is there anything that you can speak to that we're getting out of this on a day-by-day basis?
Yeah, so I will try my best. So, in the Earth, we got all the humans, we can live on the ground of the Earth pretty normally, because we got all the atmosphere. They can protect us from those strong solar radiations. But so if we can understand our atmosphere, especially upper atmosphere, those protections better, we can maybe do those similar measurements from Mars or Jupiter or other, like say, planets. And then we can, using the similar techniques or the science principles, maybe we can study whether there's life living on their ground of their planets. I think that's the answer I can think of right now. That's very broad, but if we can understand that.
But I like that answer very much. And I always like to highlight the classes, because there's a lot of emphasis in programs, especially for high school groups. What's the concrete, tangible benefit of this? And I always like to push it back to the students to say that when people do research for its own sake, when we seek to understand more about the world, our atmosphere, the universe at large, the benefits from that come in the most unexpected ways. My classic example of this is CRISPR. We were literally studying the bacterial immune system, how bacteria fight off viruses, and we developed the most incredible genetic technology of all time. People were studying information science. How can we translate an idea or pictures into zeros and ones? And everyone thought, what's the point of that? Now we all have computers and we're talking with people live in Antarctica. So it's really amazing what pure research for its own sake can benefit mankind in general. So I love that question. Yingfei, time flies and you're having fun. We're going to take two more questions before we wrap up. A class on YouTube wants to know, what is it like living there? You're getting the chance to be in Antarctica and do research there. For you personally, how do you feel about living down there?
I think it's pretty normal as in Colorado, because you got also very cold weather. Just you have to wear a lot more, of course, because right now it's much colder. But usually you just follow your normal lives. You do your job and you also read papers, do some research, and you just have regular meals, do some exercise when you got time, and sleep, of course. And sometimes you definitely got to like watch some videos and say some watch Reddit, those kind of stuff. So pretty normal, but you can definitely see those amazing views, say all the mountains, all those penguins. That's pretty interesting.
There are not many penguins in Colorado, but I do want to note, I'm not sure whether Coloradans in general would find this a great analogy or not, but we're going to say, Yingfei told us, Antarctica, just like Colorado, okay? That's our slogan for today's program. There you go. If you're in Boulder, if you're in Denver, you might as well be in Antarctica, and you can head down there anytime. We've got a great question from our chat, and then we'll wrap this up in just a minute. How does the LIDAR system decide what type of metal it's looking at? So when you shoot the laser, how does it know? Is there a special scientific way of understanding this that you can share with us?
Because that's why I mentioned earlier, we have to control our laser frequency, or you say the wavelengths, pretty accurately. We can make sure only this kind of laser of this kind of frequency, it can excite this kind of metal species and can make the metal species from ground state to the excited state, and those metal can give us the signal back. That's why we have to control our laser frequency pretty accurate.
So when you're looking for sodium, say, you'd fire basically the sodium laser up. When you're looking for a different metal, you'd fire the different wavelength laser up, and then
different wavelengths. Yeah.
Perfect. Okay.
Yeah.
There you go. Great question, guys. Yingfei, is there any last message you want to share with classes about the work that you're doing? Anything that you want them to leave with from today's broadcast about the work that you're doing?
Maybe I just want to thanks Dr. Chu for giving me this opportunity to come here to do the all research. And of course, if you can check on the CIRES website, you can definitely find Dr. Chu's group. And we are all there. We got paper published, and we got all our group members there. And you can always follow up with all the latest thing happened in our group. Yeah.
I must say, Yingfei, one of my very favorite things about having Chinese speakers on the broadcast is that universally, when people come from China, they are so grateful to everyone around them. It's like a universal thing we've had in 7 years of this program. I've never had someone on personally who's spent so much of their program talking about how great everyone around them is and how fantastic those collaborations are. So thank you for that. I think that's a really important thing in science to recognize, is that when you end up doing science and getting to go to places like Antarctica, you are working with an international community of people that are working to understand the world and universe around you. And that's a really special part about becoming a scientist, helping to share it with the world. And so Dr. Chu, the whole team, everyone can check out the CIRES website to learn more about them. But Yingfei, I want to say thank you so much for spending so much time with us today. We really appreciate it as you wrap up your day before going to bed during the day down there. And I encourage all our classes to check out the Science Show Share program of CIRES. If you want to learn more about the stuff that they're doing there, check out our McMurdo series. We've got one more program on November 15th with Aranima Prakash. She's going to talk about intro to space weather, so we're really excited about that. And Yingfei, what we do to end every broadcast, I'm going to bring back in Daniela as well so she can join in the fun. But we're going to bring in all our classes to say a big thank you and farewell. So Miss Henderson, Miss Evans, Miss Dupuis, Miss Delgado, thank you so much, everybody. Have a wonderful day. And bye for now, guys. Thank you so much.
Bye. Thanks, everybody.
Thanks.